Modules and Homological Algebra, Lecture 22, Diagram Lemmata. Today, we will formulate and prove a couple of technical classical homological statements, which can be viewed as some conclusions based on certain commutative diagrams, and the classical approach to all proofs will be the so-called diagram chase. We start with a statement which is usually called the for lemma. Consider the following commutative diagram of abelian groups with exact rows. What we have here is the following. So we have two parts of complexes of length 4. So we have the complex A dot with the differential D dot, and the complex B dot with the differential partial dot, and a morphism F from the complex A to the complex B. But we don't see the whole complex, we only see the part with positions 1, 2, 3, and 4. So we have only 4 positions in the complex A, 4 positions in the complex B. We assume that both the first row and the second row are exact, and that the diagram commutes. And the fact that the diagram commutes means that F is a morphism from the complex A to the complex B. So now the conclusion of the lemma. Claim 1, if we assume that F1 and F3 are epic and F4 is monic, then F2 is epic. Claim 2, if we assume that F2 and F4 are monic and F1 is epic, then F3 is monic. Remark. Please recall that for abelian groups, monics are injective and epics are surjective. So today, we will work with abelian groups, and we will use the terms monics interchangeably with the term injective, and similarly epics interchangeably with the term surjective. So we will prove the first claim of this lemma, and to prove the second claim is an exercise. So here is a diagram which we have, and we assume that F1 and F3 are surjective, and that F4 is injective, and we want to prove that F2 is surjective. So in order to prove that F2 is surjective, we need to prove that any element B in B2 has a preimage under F2. Let us first assume that applying the differential partial 2 to B, we get 0. Then, since the second row is an exact complex, the element B has the form partial 1 applied to X, for some element X is B1. Now, since we assume that F1 is surjective, the element X has the form F1 applied to Y, where Y is some element in A1. Due to the commutativity of our diagram, we can write the element B, which is partial 1 applied to F1 of Y, as F2 applied to D1 of Y. And this manifestly belongs to the image of F2, because this is F2 applied to some element. In other words, if B is killed by the differential, and B is an element in B2, then this definitely belongs to the image of F2. Great. Now let us move to the general case. We look at the same diagram, and now we assume that we have an element B in B2 such that partial 2 of B is not 0. So this is a non-zero element of B3. We assume that F3 is surjective. This means that there exists an element A in A3 such that F3 of A is equal to partial 2 applied to B. Now we do the computation. If we apply F4 to D3 of A, then, due to the commutativity of our diagram, we can rewrite it as partial 3 applied to F3 of A, but F3 of A is partial 2 of B. So this is equal to partial 3 of partial 2 of B, and this is 0 because the second row is a complex. Therefore, since we have assumed that F4 is injective, we have that the element D3 of A is necessarily 0, because if we apply a 4 to it, we will get 0. But then this means that the element A belongs to the kernel of D3. Since we have assumed that the first row is exact, this means that we can write A as D2 of some element C in A2. Now we can compute that partial 2 applied to B is the same thing as F3 applied to A, and this is the same thing as F3 applied to D2 of C. And now by commutativity, this is the same thing as partial 2 applied to F2 of C. So the elements B and F2 of C, they have the same image under partial 2. In other words, partial 2 annihilates their difference. But then, due to the fact which we already proved on the previous slide, the difference B minus F2 of C belongs to the image of F2. So it can be written as F2 of some element D in A2. Moving F2 of C to the other side, we write B as the image of C plus D under F2, which manifestly belongs to the image of F2. And this completes the proof. The 4 lemma has a number of consequences, and one of them is what is classically called as the 5 lemma. So this is a corollary from the 4 lemma. Consider the following commutative diagram of abelian groups with exact rows. We have a similar diagram as for the 4 lemma, but it is one step longer. So we have the complex A with differential D, the complex B with differential partial, and the morphism F between these two complexes, and we write the 5 components of these complexes. And now the claim. If we assume that F2 and F4 are isomorphisms, F1 is epic and F5 is monic, then F3 is an isomorphism. There is also a weak version of this lemma. If we assume that F1, F2, F4, and F5 are isomorphisms, then F3 is an isomorphism. Proof? In order to prove this, we just apply the 4 lemma to the 4 subdiagrams of this diagram. So if we apply it to the left subdiagram, we have that F2 and F4 are isomorphisms, and F1 is epic. This means that F3 is monic. If we applied it to the right-hand side, 4 subdiagram, we have that F2 and F4 are isomorphisms, and F5 is monic. This means that F3 is epic. So F3 is both monic and epic. So it is both injective and surjective. So it is bijective. So it is an isomorphism. This establishes the 5 lemma. There is a classical corollary from the 5 lemma, which is called the 3 lemma. This goes as follows. Consider the following commutative diagram of abelian groups with exact rows. So we have 2 short exact sequences and the morphism F between them. So the assertion is as follows. If we assume that the left morphism F1 and the right morphism F3 are isomorphisms, then the middle morphism F2 is also an isomorphism. Proof? This, of course, follows directly from the 5 lemma as soon as we complete it to a 5 sequence by adding the 0 morphism between 0 objects on the left and the 0 morphism between 0 objects on the right. Then we are in the situation of the 5 lemma because the 0 morphisms are isomorphisms and F1 and F3 are assumed to be isomorphisms. So this is just a special case of the weak formulation of the 5 lemma. Okay, now let us go to the next lemma, which is kind of much bigger. This is usually called the 3 times 3 lemma, and it is also known as a 9 lemma. So now we consider the following commutative diagram of abelian groups with exact rows. So we have 3 rows, the row A, the row B, and the row C, and these are short exact sequences with differentials D, partial, and delta, respectively. And then we have morphism F of complexes from the sequence A to the sequence B, and the morphism G of complexes from the sequence B to the sequence C. And then we complete this picture by zeros on top and by zeros in the socle. So this is a commutative diagram, and all rows are exact. The claim: if we assume that two left columns are exact, then the remaining right column is also exact. Similarly, if we assume that the two right columns are exact, then the remaining left column is also exact. And of course, we will prove only the first claim, and the second claim is an exercise. So here is the short version of the diagram. The three rows are short exact sequences, and the left two columns are short exact sequences, and we want to prove that the rightmost column is also a short exact sequence. First of all, let us look at the exactness at A3, at this position, for the right column. This is, of course, equivalent to the claim that F3 is an injective map. Okay, let A be an element in A3 such that F3 of A is equal to 0. Then we can write A as d2 of x for some element x in A2, because d2 is surjective. Now we have Z0, which is the image of A under F3, can be written as F3 applied to d2 of x, and due to the commutativity of our diagram, this is equal to partial 2 applied to F2 of x. This means that F2 of x belongs to the kernel of partial 2, and so it should be in the image of partial 1, because the second row is exact. So there is y in B1 such that F2 of x is equal to the partial 1 of y. Next, let us look at G1 applied to y. So if we apply delta 1 to G1 of y, then due to the commutativity of our diagram, we can rewrite it as G2 applied to partial 1 of y. Now partial 1 of y is F2 of x, so this is equal to G2 applied to F2 of x, and this is 0 because the middle column is a complex. Therefore, G1 of y is 0 because delta y is an injective map. The third row is exact. Therefore, we can write y as f1 of z because the first column is exact. So here z is some element in A1. So now we look at the top left square. So applying partial 1 to f1 of z, we have the same as we get when we apply f2 to d1 of z. So this is due to the commutativity of our diagram. Consequently, f2 applied to d1 of z is equal to f2 of x. And thus, x is equal to d1 of z because f2 is an injective map. The second column is exact. But this means that our element of A is equal to d2 of x, which is equal to d2 of d1 of z, and this is 0 because the first row is a complex. And we are done. So if A is sent to 0 by F3, then A itself is 0. So F3 is an injective map. So we have just proved exactness at the position A3. Now let us move to the position C3. So here is our diagram. We now included that the map from A3 to B3 is injective. So in this diagram, now if you look at it, in the lower right square, we have that delta 2 after G2 is equal to G3 after partial 2. This is just the commutativity of this square. Also, both delta 2 and G2 are known to be surjective by the assumptions. So their composition is surjective. The composition of surjective maps is surjective. But this means that G3 after partial 2 must be surjective, which implies that G3 must be surjective. So this implies exactness at the position C3. So what remains is to prove exactness at the position B3. 3. So now let us prove this exactness at the position B3. In fact, let us first check that the rightmost column is a complex, that the composition of G3 after F3 is 0. So let's check that. Start with any A in A3. Then we can write this A as D2 of some X in A2, because D2 is surjective. Now, G3 of F3 of A can be written as delta 2 of G2 of F2 of X, due to the commutativity of our diagram. But of course, G2 of F2 of X is 0 because the middle column is a complex. This means that G3 of F3 of A is 0, and so G3 after F3 is the 0 map. We have just checked that the rightmost column is a complex. Finally, let us prove exactness at B3. Let B be an element in B3 which is mapped to 0 by G3. Then, since partial 2 is surjective, we can write B as partial 2 of X for some X in B2. Now we use the commutativity of our diagram and write delta 2 of G2 of X as G3 of B. So this is G3 of partial 2 of X. Well, we have assumed that G3 of B is equal to 0. This means that G2 of X belongs to the kernel of delta 2. Since the last row is exact, this means that G2 of X is equal to delta 1 of some element C in C1. Since G1 is surjective, we can write C as G1 of Y, where Y is an element in B1. So this implies that G2 applied to X minus partial 1 of Y is equal to 0. And partial 2 applied to X minus partial 1Y is equal to the partial 2 of X, and this is equal to B. Now we use this and get that the element X minus partial 1 of Y is in the image of F2, so we can write it as F2 of some element Z in A2. This is because it is sent by G2 to 0, and the middle column is exact. And so now we can write our element B as partial 2 applied to F2 of Z, which is equal to F3 applied to D2 of X using the commutativity of the top right square of our diagram. And so we see that the element B belongs to the image of F3. And this completes the proof. So this proves our 3 times 3 lemma. And the final lemma which we are going to talk about today is called the snake lemma. So here is the short formulation of the snake lemma. Consider the following commutative diagram of abelian groups with exact rows. So we have row 1, A1, A2, A3, and 0, with differentials d1 from A1 to A2 and d2 from A2 to A3. And then we have the second row, 0, B1, B2, B3, with differential partial 1 from B1 to B2 and partial 2 from B2 to B3. And then we have the homomorphism of complexes, F1 from A1 to B1, F2 from A2 to B2, and F3 from A3 to B3, so which make this diagram commutative. So we have such a diagram, and the claim is that this diagram induces an exact sequence as follows. So we start from the kernel of F1, we go to the kernel of F2, then to the kernel of F3, then there is a certain map called kappa from the kernel of F3 to the cokernel of F1, and then we can go to the cokernel of F2 and to the cokernel of F3. And this map kappa is usually called the connecting morphism. And now we can put it all in one big diagram, which also explains the name, the snake lemma. So if we put the kernels of F1 and F2 and F3 on top, and the cokernels here in the bottom, then the connecting morphism kappa is a map from the kernel of F3 to the cokernel of F1, and when you draw it, then you have something which looks like a snake. So this is the reason why this is called a snake lemma. So we have such a long sequence with 6 terms, and the claim that the sequence is exact in all 4 middle terms. Let us first talk about the easy part of the proof. The map from the kernel of f1 to the kernel of f2 is just the restriction of d1 from a1 to a2 to the kernel of f1. And similarly, the map from the kernel of f2 to the kernel of f3 is just the restriction of d2 from a2 to a3 to the kernel of f2. And that the composition of these two maps is 0 follows directly from the assumption that d2 after d1 is 0. And that this construct is exact at the kernel of f2, this is proved similarly to the 3 times 3 lemma. So we leave this as an exercise. And in the dual part of the complex, so the cokernel part, and we have the induced maps between the cokernels, this is completely similar, or can be obtained by reversing all errors in our diagrams. So the really interesting part is the one which is connected to the connecting homomorphism kappa. So let us define this kappa. So this is our big snake diagram. So let us take an element A in A3, which belongs to the kernel of F3. So F3 of A is 0. Since D2 is surjective, we can write A as D2 of some x in A2. Note that due to the commutativity of our diagram, partial 2 applied to F2 of x is equal to F3 of A, and this is 0 by our assumption on A. Therefore, since our second black row is exact, there is an element y in B1 such that F2 of x is equal to partial 1 applied to y. Moreover, since partial 1 is an injective map, this y is certainly unique. Now we define kappa of A as the image of y in the cokernel of F1. That's great, but of course we made some choices during our process, namely we choose x in A2. So we need to argue why this kappa of A is well defined. That is, it does not depend on our choice of x. There was no choice in y was unique, but we have chosen some x. So if we choose a different x, so the difference between different choices of x will be an element in A2 which goes to 0 when we apply D2 to it. Since our first sequence is exact in A2, this means that any difference in the choice of x is given by the image of some element z in A1 under D1. But any element z in A1 contributes to 0 when this is mapped to the cokernel of F1. So different choices of x are controlled by elements in A1, but elements in A1 are mapped to the 0 element in the cokernel of F1. So this means that kappa of A is well defined. So this establishes our definition of kappa. Of course, one needs to check that kappa, which is defined in this way, is a morphism of abelian groups. That's an exercise. Now let us check that this map kappa, which we defined in this way, gives us a complex. So which means that kappa, after the morphism from care of F2 to care of F3, is 0. So we will check that. And then kappa, followed by the morphisms between cokernel of F1 and cokernel of F2, that's also 0. That is an exercise. If we have some element A in A3, which belongs to the kernel of F3, and which comes from an element x in the kernel of F2, then in the definition of K, we have that the element partial 1 applied to y from that definition is equal to F2 of x, and then this is 0, because f is in the kernel of F2. Therefore, our element y is 0 due to the injectivity of partial 1. This is exactness of the second black sequence at B1. Therefore, directly from the definition, we have that kappa of such A is 0. And similarly, sending kappa of A for any A in the kernel of F3 to the cokernel of F2 gives 0. And this indeed means that we have a kernel-cokernel complex. Our kernel-cokernel sequence is indeed a complex with our definition of kappa. Now let us check exactness at the position kernel of F3. And one also needs to check exactness at the position of cokernel of F1, and this is similar and left as an exercise. So now we have our diagram, and we assume that A is an element in the kernel of F3, such that kappa of A is 0. This means that the corresponding Y in B1 belongs to the image of F1. Therefore, there is Z in A1 such that F1 of Z is equal to Y. But then, D1 applied to Z and X in A2 from our construction of kappa of A, they have the same images under F2. And therefore, the difference between our X and D1 of Z belongs to the kernel of F2. The image of this difference in the kernel of F3 equals A because D2 after D1 is 0 and D2 of X is equal to A. So we can now replace in our definition of kappa of A, so we can replace A by this difference, and we get that A is in the image of the induced map from the kernel of F2 to the kernel of F3. And this proves exactness of our kernel-cokernel sequence at the term kernel of F3. Some problems and questions at the end. Problem question 1. Prove with all details the second claim of the 4 lemma. Problem question 2. Prove with all details the second claim of the 3 times 3 lemma. Problem question 3. Formulate and prove analogues of the 3 lemma for monics and epics separately. Problem question 4. In the proof of the snake lemma, define with all details the maps from the cokernel of F1 to the cokernel of F2, and from the cokernel of F2 to the cokernel of F3, and prove exactness of these at cokernel of F2. Problem question 5. Check that the connecting homomorphism kappa is a homomorphism of abelian groups. Thank you very much, and see you next time.